Good day and welcome to Big Bad Tech. I'm instructor Jim Pytel, and today's topic of discussion is doubly fed induction motors. Our objective is to examine doubly fed induction motors. We'll examine several different operational modes and how by varying rotor excitation frequency, one can control the resultant rotational speed of doubly fed induction motors. Just when you thought you'd seen the last of wound rotor induction motors, along comes a doubly fed induction motor, which I know is just going to blow your freaking mind. If you've been following this lecture series in intended sequence, you'll recall we already examined squirrel cage induction motors and asynchronous generators, electrically excited synchronous motors and synchronous generators, and wound rotor induction motors in some detail. If we're to follow a predictable pattern, we should be driving straight into the generator aspect of wound rotor induction motors, but we're not. We're going to take an entertaining detour. Not only is this sidetrip entertaining, it's an important preamble to the upcoming doubly fed induction generator, since doubly fed induction generators are a natural extension of doubly fed induction motors. You'll no doubt recall wound rotor induction motors are very similar to squirrel cage induction motors, only the rotor, rather than being cast aluminum or copper cage-like structure, is composed of wire windings, hence the name. Additionally, wound rotor induction motors feature slip rings and brushes which allow access to the rotor. In the aforementioned wound rotor induction motor lecture, we explored how varying the resistance of the induction-operated rotor can change the motor's operational characteristics under load. As cool as this is, it is not the only trick this animal can do. Given both the rotor and stator are accessible, there's a range of tricks wound rotor induction motors can do you've probably never thought of, each more insane than the next. We are already intimately familiar with the traditional induction mode of operation. In this mode, the rotor windings are connected together with or without external resistors, and three-phase AC is applied to the stator. In this mode of operation, induced current flows in the rotor windings, which creates its own magnetic field, which is attracted to the stator rotating magnetic field, and the rotor follows it around and around and around. Central to the induction mode of operation is quite obviously induction. This means the rotor must slightly lag the stator even in the unloaded state. In induction mode, the rotor speed varies as a function of applied torque. Additionally, it's possible to change rotational direction by swapping any two phase sequences. But wait, that's not all. Given the stator and rotor windings are both accessible in wound rotor induction motors, what if we flip this concept on its head? Rather than supplying the stator with AC, we instead supply the rotor with AC. And rather than tying the rotor windings together, instead tie together the stator windings. Sure, go ahead, knock yourself out. This is still an induction motor, and it behaves identically to the traditional induction configuration, albeit rotational direction is reversed. For example, if we applied phase sequence 1, 2, 3 on the stator, initiated clockwise rotation, the same applied phase sequence 1, 2, 3 on the rotor would initiate counterclockwise rotation. More weirdness awaits. Think back to the principal difference between induction and synchronous motors. Induction motors operate via induction and exhibit variable speed as a function of load torque, whereas synchronous motors have a magnet on the rotor that locks into the stator at constant speed. Electrically excited synchronous motors get that magnet on the rotor by exciting the rotor field winding with DC electricity through a set of slip rings. In summary, a synchronous motor has AC on the stator and DC on the rotor. Are you thinking what I'm thinking? I think so. Given both sets of windings are accessible in wound rotor induction motors, can't we excite the stator with AC and the rotor with DC and use it like a synchronous motor? Sure thing. This also works. When the rotor is excited with DC, it creates a fixed electromagnet on the rotor, which locks into the stator. As with synchronous motors, wound rotor induction motors operated in synchronous mode exhibit constant speed inside their operational range, pull-out torque roughly proportional to field excitation current magnitude, and the ability to control reactive power requirements based on field current magnitude. Additionally, wound rotor induction motors operated in synchronous mode necessitate the same starting circuits characteristic of synchronous motors due to the same complications we explored in the synchronous motor starters lecture, available at the Big Bad Tech channel. Now, before you run out and just grab an off-the-shelf DC power supply and hook it to the rotor, let me caution you, this is not without its associated challenges. First, ensure the rotor windings you're making use of are rated for DC operation. Viewers will recall inductive impedance is a frequency-dependent phenomenon where the inductive impedance magnitude Z sub L is equal to 2 pi FL. What's the frequency of DC? 0 hertz. This means these rotor windings will not present any inductive impedance to a DC source, and given only the small resistive impedance, field current could reach unacceptably high values and damage the rotor windings. For this reason, it's imperative to manage field current magnitude by carefully monitoring DC exciter voltage and/or placing some resistance in series with the rotor windings. The second challenge of applying DC voltage to a wound rotor induction motor rotor is the simple challenge of where to hook it. Oftentimes, rotor windings are only accessible at one end and lack access to the central node of a Y configuration. Think about it. A DC source has two connections, positive and negative, where the rotor has three, M1, M2, and M3. You might initially suspect you just grab any two rotor windings, but that would result in a wonky rotor magnetic field only 2/3 of its intended strength. One way of getting around this connection challenge is by placing windings M1 and M2 in parallel with one another, and this parallel combination is in series with M3. Given the direction of conventional current travel and the polarity markers in windings M1 and M2, this creates a shared fixed north pole, and winding M3 creates a fixed south. It's still wonky, but not nearly as wonky as 2/3 of a rotor electromagnet. While we're still in synchronous mode, what if we flip this concept on its head? Rather than supplying the stator with AC, we instead supply the rotor with AC. And rather than supplying the rotor with DC, we instead supply the stator with DC. This is also still a synchronous motor, and it behaves identically to the traditional synchronous configuration, albeit rotational direction is reversed. For example, if applied phase sequence 1, 2, 3 on the stator initiated clockwise rotation, the same applied phase sequence 1, 2, 3 on the rotor would initiate counterclockwise rotation. So far, we've discussed two induction modes, traditional AC on the stator and an induction rotor, and a flip-flopped alternate configuration with AC on the rotor and an induction stator, and two synchronous modes, traditional AC on the stator and DC on the rotor, and a flip-flopped alternate configuration with AC on the rotor and DC on the stator. Before we discuss the remaining mode, I'll let you in on a little secret. As comparable as the flip-flopped alternate configurations are to the traditional configurations, you're never going to run into them. And if you do, the only reason it's being used is for the same reason over 50 retired accountants put ape hangers and loud pipes on motorcycles, i.e., they're attention-seeking jerks. Don't be a jerk and use the traditional configuration. You'd think that'd be all there is to say, but more weirdness awaits. Given this lecture is entitled Doubly Fed Induction Motors, you'd think there'd be more to say about induction mode, but there is not. Because the super extended play bonus round I'm about to show you is really an extension of synchronous mode, albeit for some weird reason, people incorrectly refer to it as induction. What I'm about to show you is not induction. This is yet another synchronous mode, and perhaps the most useful of the different doubly fed induction motor configurations. The mode I speak of applies fixed frequency 3-phase AC to the stator and variable frequency 3-phase AC to the rotor using a power electronics device known as an AC to AC converter. We'll examine the power electronics devices central to the operation of an AC to AC converter, rectifiers and inverters in greater detail in later lectures. However, as a summary of the process, an AC to AC converter accepts incoming 3-phase AC with fixed magnitude and fixed frequency, rectifies it to all DC, then inverts this incoming DC to variable 3-phase AC with user adjustable magnitude and frequency, meaning the AC to AC converter can subject the rotor to high voltage, high frequency AC, low voltage, low frequency AC, or any other combination of voltage, magnitude, and frequency in between. As with the stator, 3-phase AC on the rotor creates a rotating magnetic field. The two rotating magnetic fields lock into one another and the rotor is physically dragged along. Again, even though in practice this is called a doubly fed induction motor, I must again remind the viewer this is still synchronous operation. As a means of demonstrating my point, let's begin with slow motion analysis of regular synchronous operation, i.e. fixed DC. With fixed 0 Hz DC applied to the rotor, the physical position, symbolized by a circle, and the rotor electromagnet, symbolized by a red arrow, are one in the same. If the stator rotating magnetic field, symbolized by a white arrow, moves 90 degrees clockwise, the rotor is physically and electromagnetically dragged along 90 degrees clockwise as well. If the stator rotating magnetic field moves 180 degrees clockwise, the rotor is physically and electromagnetically dragged along 180 degrees as well. If the stator rotating magnetic field moves to 270 degrees, the rotor is physically and electromagnetically dragged along 270 degrees as well. Long story short, if the stator rotating magnetic field makes one full 360-degree revolutions clockwise, the rotor is similarly physically and electromagnetically dragged along for one full 360-degree clockwise revolution as well. If the stator does 12 turns, the rotor does 12 turns. Makes sense. Now, instead of fixed DC, let's apply three-phase AC to the rotor. In this scenario, the rotor's physical position and the electromagnet are not tied together anymore. There's two possible choices. The rotating magnetic field on the rotor can go in the same direction as the stator or opposite to it. Let's examine the same direction operation first. Consider the rotor and stator magnetic fields separately, and consider what happens if we apply regular fixed frequency AC to the stator and super slow three-phase AC to the rotor, such that the electromagnet on the rotor moves, let's say, 30 degrees clockwise, at the same time it takes the stator to complete one full 360-degree revolution clockwise. Now let's look at what happens when these two electromagnets interact. Taken together, a quarter of the way through the cycle, the rotor and stator magnetic fields are still locked together, but the rotor physical position is a quarter of 30 degrees, or 7.5 degrees behind. Halfway through the cycle, the rotor and stator magnetic fields are still locked together, but the rotor physical position is now 15 degrees behind. 3/4 of the way through the cycle, the rotor and stator magnetic fields are still locked together, but the rotor's physical position is 22.5 degrees behind. All the way through the cycle, both the rotor and stator magnetic fields made a full 360, but the rotor is physically 30 degrees behind, such that it completes only 330-degree turn every time the stator does a full 360. After 2 full turns of the stator, the rotor would be 60 degrees behind, 3 turns in the stator, 90 degrees, and so on. 12 full turns later on the stator, and the rotor only completes 11 turns in the same time period. See what happened? The rotor slowed down. Let's say this was still too fast. If we wanted to slow the rotor down even more, one could slightly increase the rotor excitation frequency such that the electromagnet is further displaced, let's say 60 degrees clockwise, in the same time it takes the stator to complete one full revolution. Taken together, a quarter of the way through the cycle, the rotor and stator magnetic fields are still locked together, but the rotor's physical position is a quarter of 60 or 15 degrees behind. Halfway through the cycle, the rotor and stator magnetic fields are still locked together, but the rotor physical position is now 30 degrees behind. 3/4 of the way through the cycle, the rotor and stator magnetic fields are still locked together, but the rotor's physical position is 45 degrees behind. All the way through the cycle, both the stator and rotor magnetic fields made a full 360, but the rotor's physical position is 60 degrees behind. In summary, for every full cycle in the stator, the rotor physically only moves 300 degrees. 12 full turns in the stator, and the rotor would only complete 10 turns in the same direction. Again, the rotor slowed down. Given the rotor rotating magnetic field and the stator rotating magnetic field traveling in the same direction, in this case clockwise, one might draw the conclusion that the physical movement of the rotor is dependent on only the difference of the rotor rotating magnetic field and the stator rotating magnetic field. Long story short, when fixed frequency three-phase AC is applied to the stator and variable frequency three-phase AC is applied to the rotor in the same rotational direction, the resultant rotor speed is dependent upon this formula, where the rotor speed is equal to 60 times the difference of the stator frequency and the rotor frequency divided by the number of pole pairs per phase. Consider regular synchronous operation where DC is considered to have an excitation frequency of 0 Hz. Let's say we're using a 2-pole pair per phase motor with fixed frequency 60 Hz AC applied to the stator. Application of the doubly fed induction motor rotor speed formula demonstrates the rotor should move at 1800 RPM. Exactly what we'd expect for traditional synchronous operation for a 2-pole pair per phase construction. What if we applied fixed frequency 60 Hz AC to the stator and super slow 1 Hz AC to the rotor in the same direction? Another application of the doubly fed induction motor rotor speed formula demonstrates the rotor should move at 1770 RPM. What if we kept 60 Hz AC applied to the stator and ramped up excitation frequency to the rotor in the same direction in 1 Hz increments, 1 to 2, 2 to 3, 3 to 4, and so on? Successive applications of the doubly fed induction motor rotor speed formula demonstrates the rotor should move at 1740 RPM, 1710 RPM, 1680 RPM, and so on, decreasing in 30 RPM steps for every 1 Hz increase. If you think about it, given both magnetic fields are revolving in the same direction, the rotor is essentially responding to the resultant differential between them. In traditional synchronous operation with 60 Hz in the stator and pure 0 Hz DC on the rotor, it operates like a 2-pole pair per phase synchronous motor at 60 Hz. With 60 Hz in the stator and 1 Hz in the rotor, it operates like a 2-pole pair per phase synchronous motor operated at 60 minus 1 or 59 Hz. With 60 Hz in the stator and 2 Hz in the rotor traveling in the same direction, it operates like a 2-pole pair per phase synchronous motor operated at 60 minus 2 or 58 Hz, and so on. You might think of this in relative terms. Let's say a car traveling at 60 miles per hour passes a stationary car. Understandably, there's a 60 mile per hour differential. Now let's say the same car traveling at 60 miles per hour passes another car traveling the same direction at 10 miles per hour. Understandably, there would only be a 50 mile per hour differential between these two cars, and so on. In summary, given fixed frequency AC on the stator, if we speed up the excitation frequency of the rotor in the same direction, the differential between the two rotating magnetic fields decreases and the rotor physically slows down. This is known as sub or hyposynchronous operation. As the prefixes sub or hypo are meant to imply, given both rotating magnetic fields traveling in the same direction, the resultant rotor speed is less than what it would ordinarily be than in traditional synchronous operation. As you might have guessed it, there is another mode known as super or hypersynchronous operation, which necessitates the rotating magnetic fields to travel in opposite directions. As with our previous discussion, the rotor's physical position and electromagnet aren't tied together. Consider fixed frequency 3-phase AC applied to the stator, such that the stator rotating magnetic field turns one full revolution clockwise. However, super slow frequency 3-phase AC applied to the rotor, such that it moves 30 degrees counterclockwise or negative 30 degrees in the same time period. Taken together, a quarter of the way through the cycle, the rotor and stator magnetic fields are still locked together, but the rotor physical position is 7.5 degrees ahead. Halfway through the cycle, the rotor and stator magnetic fields are still locked together, but the rotor physical position is now 15 degrees ahead. 3/4 of the way through the cycle, the rotor and stator magnetic fields are still locked together, but the rotor's physical position is 22.5 degrees ahead. All the way through the cycle, both the rotor and stator magnetic fields made a full 360, but the rotor is physically 30 degrees ahead, such that it completes a full turn plus 30 every time the stator does a full 360. 12 full turns in the stator, and the rotor completes 13 turns in the same time period. See what happened? The rotor sped up. You might be tempted to rewrite the doubly fed induction motor rotor formula for hypersynchronous operation, but as long as you keep polarity in mind, our original formula will work quite well. Viewers will recall in the mechanical power lecture, we defined clockwise as positive and counterclockwise as negative. As previously, what if we applied fixed frequency 60 Hz AC to a stator with 2 pole pairs per phase in the clockwise or positive direction, and super slow 1 Hz AC to the rotor in the opposite or counterclockwise direction? If you think about it, that's negative 1 Hz. An application of the doubly fed induction motor rotor speed formula demonstrates the rotor should move at 1830 RPM, 30 RPM faster than the regular synchronous speed for a 2-pole pair per phase motor at 60 Hz. Hence the title Hypersynchronous. What if we kept 60 Hz AC applied to the stator in clockwise direction, ramped up excitation frequency to the rotor in the opposite direction in negative 1 Hz increments? Successive applications of the doubly fed induction motor rotor speed formula demonstrates the rotor should move at 1860, 1890, 1920 RPM, and so on, increasing in 30 RPM steps, each negative 1 Hz increment. If you think about it, given two magnetic fields revolving in opposite directions, the rotor is again responding to the resultant differential between them. In traditional synchronous operation with 60 Hz in the stator and pure 0 Hz DC on the rotor, it operates like a 2-pole pair per phase synchronous motor at 60 Hz. With 60 Hz in the stator and negative 1 Hz in the rotor, it operates like a 2-pole pair per phase synchronous motor operated at 60 minus 1 or 61 Hz. With 60 Hz in the stator and negative 2 Hz on the rotor going the opposite direction, it operates like a 2-pole pair per phase synchronous motor operated at 60 minus 2 or 62 Hz, and so on. Again, you might think of this in relative terms. Let's say a car traveling at 60 miles per hour passes another car traveling at 10 miles per hour in the opposite direction. Understandably, there'd be a 70 miles per hour differential between these two opposite moving cars, and so on. I must remind the viewer that regardless of the mode employed, traditional synchronous mode with fixed frequency 3-phase AC in the stator and 0 Hz DC on the rotor, hyposynchronous mode with fixed frequency 3-phase AC on the stator and variable frequency 3-phase AC on the rotor traveling in the same direction, or hypersynchronous mode with fixed frequency 3-phase AC in the stator and variable frequency 3-phase AC in the rotor traveling in the opposite directions. All of these are synchronous modes of operation, not induction, because the rotor electromagnet remains locked in with the stator rotating electromagnet despite the variability of the rotor's physical speed. Given this observation, hyposynchronous and hypersynchronous modes share characteristics identical to traditional synchronous operation with regard to field current and pull-out torque, line current, and reactive power requirements. Viewers will recall pull-out torque. The torque at which synchronous motor loses synchronization is roughly linearly dependent upon field current. As field current increases, so does pull-out torque until it reaches saturation, while pull-out torque eventually flatlines. Additionally, we learned by varying field current, one can also observe changes in line current and reactive power consumption for a given load condition. Under-excitation of the rotor means the stator draws reactive power as would an inductive load. In contrast, over-excitation of the rotor means the stator supplies negative reactive power as would a capacitive load. A graph of reactive power as a function of field current looks something like this, which identifies an important operating point. At a given load condition, field current can be so managed that the motor neither draws nor supplies reactive power, and voltage and current are perfectly in phase with one another. This would be occasion of unity power factor and minimum line current. Lastly, we learned that starting synchronous motors necessitating synchronization between the stator and rotor magnetic field isn't as easy as one might initially suspect, principally because upon the closure of a full voltage starter, the stator rotating magnetic field is instantaneously established at full speed, whereas the rotor and applied load with some level of static inertia may take some time to come up to this speed. For this reason, one might need to resort to some cunning trickery to either speed up the rotor or slow down the stator. We explored several synchronous motor starting methods in the Synchronous Motor Starters lecture, available at the Big Bad Tech channel. All these properties remain true for doubly fed induction motors in hyposynchronous and hypersynchronous operation, and I'll not repeat myself today. I will, however, take the time to caution you that in these modes you need to pay attention, because you're not supplying the rotor with DC anymore, but rather a variable frequency AC. This means you gotta watch out for frequency-dependent phenomenon like inductive impedance. Viewers will recall inductive impedance magnitude Z sub L is equal to 2 pi FL. Gee, where have I heard that before? Oh yeah, I mentioned it like 6 minutes ago. Given low frequency AC, the inductive impedance will be low. At higher excitation frequencies, inductive impedance increases. This brings us back to how field current influences pull-out torque and reactive power requirements. Let's say you're rolling along in hyposynchronous operation with fixed frequency 3-phase AC on the stator and variable frequency 3-phase AC on the rotor traveling in the same direction, and you've adjusted field current magnitude properly for a specified desired pull-out torque, line current, and reactive power requirement at that particular rotor excitation frequency, but you want the rotor to turn slower. What are you going to do? The proper response would be to increase rotor excitation frequency. That is true, but it's only part of the answer. Think about what happens at increased frequency. Yes, with increased rotor excitation frequency, the differential between the stator and the rotor rotating magnetic fields will decrease, and yes, the rotor's rotational speed will slow down, but also think about what happens to the inductive impedance of the rotor windings. Given inductive impedance is a frequency-dependent phenomenon, impedance will also increase as a result of increased rotor excitation frequency. And if you're using a constant voltage source, field current will decrease because of increased impedance. If you keep raising and you keep raising rotor excitation frequencies in an effort to slow the rotor down, at a certain point, the inductive impedance of the rotor windings will be so high and the field current so low, the rotor will reach pull-out torque too early, lose synchronization, and everything will just all go to hell, and you will fail your motors and generators class, and your imaginary girlfriend will break up with you. The point is, the AC to AC converter on the rotor shouldn't be producing just variable frequency 3-phase AC, but rather variable frequency and variable magnitude 3-phase AC. At higher rotor excitation frequencies, the AC to AC converter also needs to step up voltage due to increased inductive impedance to keep field current constant. Since this is pretty important, this is perhaps worthy of a quick practical demonstration. Along the way, we'll demonstrate how the rotational speed of a doubly fed induction motor responds to different rotor excitation frequencies. Let's first get the motor rolling in traditional synchronous mode with pure DC on the rotor and fixed frequency AC on the stator. As can be expected for a traditional electrically excited synchronous motor with 2 pole pairs per phase at 60 Hz, the rotor turns at exactly 1800 RPM. If I lightly load the motor up with 0.5 Newton meters of counter torque, given this is synchronous operation, the rotor remains turning at exactly 1800 RPM. I adjust the exciter voltage until field current reaches around 400 mA DC. In this perfectly power factor corrected state, the line current bottoms out at maybe 310 mA AC on the stator, and the stator consumes roughly 113 watts of real electrical power and neither absorbs nor supplies any reactive power. If we're to highlight this operating point on the pull-out torque, line current, and reactive power requirements as a function of field current graphs, we'd be right here, i.e. where we want to be. Minimal line current, neither under nor overexcited. Let's say I want to slow the rotor down. This is a perfect scenario for hyposynchronous operation. Instead of DC, I start supplying 2 Hz 3-phase AC to the rotor traveling in the same direction as the 60 Hz stator. The motor still exerts 0.5 Newton meters of counter torque, however slows down to 1740 RPM as we might expect. This being said, notice what happens to the rotor and stator electrical characteristics. Given I changed the frequency from 0 Hz to 2 Hz, but kept voltage magnitude the same, field current decreased from 400 mA to 370 mA because the frequency-dependent inductive impedance of the rotor went up. We've departed from our ideal operating point. As a result, line current rises and the motor starts drawing a small amount of reactive power. Let's say this is still too fast. I want to slow the rotor down. I ramp up rotor excitation frequency from 2 to 4 Hz, keeping voltage magnitude constant. The rotor slows down to 1680 RPM as we might expect. Again, notice what happened to rotor and stator electrical characteristics though. Given I increased the frequency, but inappropriately kept voltage magnitude constant, field current decreased because the frequency-dependent inductive impedance of the rotor went up. We've again further departed from our ideal operating point. As a result, line current rises and the motor starts drawing more reactive power. We are deep in underexcited territory now. You note every time field current decreased, not only did the line current and reactive power increase, resultant pull-out torque decreased. We haven't reached it yet, but we are clearly playing with fire here. If I try to slow the rotor down even further by exciting the rotor to 6 Hz AC, everything goes to hell rather quickly. At 6 Hz, inductive impedance is so high and field current is so low, the magnetic fields lose synchronization, line current skyrockets, and the motor sounds as mad as a bobcat asked to fetch. Shut her down. Long story short, this is not the way to do this. The ADC to AC converter driving the rotor shouldn't be adjusting rotor excitation frequency, but also voltage. At low excitation frequencies, when rotor inductive impedance is low, keep voltage low. At higher excitation frequencies, when inductive impedance is higher, step voltage up so field current remains in the ideal zone for proper operation and pull-out torque. This is often known as a linear volts per hertz profile, in this case including a DC offset. At DC, apply a certain voltage to get the desired field current. At 2 Hz, when inductive impedance rises, step voltage up that same linear amount to keep field current relatively constant. At 4 Hz, when inductive impedance again rises, step voltage up that same linear amount to keep field current relatively constant, and so on. Here's a demonstration of this properly managed style of doubly fed induction motor speed control. As previously, I first get the motor rolling in a traditional synchronous mode with pure DC on the rotor and fixed frequency AC on the stator. As can be expected, the rotor turns exactly at 1800 RPM. Then lightly load the motor with 0.5 Newton meters of counter torque. Given this is synchronous operation, the rotor remains turning at exactly 1800 RPM. I adjust the exciter voltage until field current reaches around 400 mA DC. In this perfectly power factor corrected state, line current bottoms out and the stator consumes roughly 113 watts of real electrical power and neither absorbs nor supplies any reactive power. If we're to highlight this operating point on the pull-out torque, line current, and reactive power requirements as a function of field current graphs, we'd be right here, i.e. where we want to be. Minimal line current and neither under nor overexcited. Let's say I want to slow the rotor down. Instead of DC, I start supplying 2 Hz AC to the rotor traveling in the same direction as the 60 Hz stator. The motor still exerts 0.5 Newton meters of counter torque and slows down to 1740 RPM as we might expect. This time, however, with a linear volts per hertz ratio, given slightly increased excitation frequency, voltage is also slightly increased and pretty much everything remains the same. field current remains high, and as a result, line current remains at a minimum, and the stator neither absorbs nor supplies any reactive power. By adjusting voltage in the same proportion as frequency, we're keeping field current where it needs to be, so this hyposynchronous motor remains inside that sweet spot. Let's perform the same speed ramp down by supplying progressively higher rotor excitation frequencies, only this time progressively increasing voltage magnitude as we do so. The idea is to keep field current, and thus line current and reactive power demands inside an ideal range. At an increased 4 Hz and a slightly increased voltage, the rotor slows down to 1680 RPM and field current remains high. Line current remains low and the stator neither absorbs nor supplies any reactive power. At an increased 6 Hz and slightly increased voltage, the rotor slows down to 1620 RPM and field current remains high and line current remains low and the stator neither absorbs nor supplies any reactive power. Check it out, we're still rolling at 6 Hz. Isn't that where it all went to hell last time? I think it was. At 6 Hz, we're rolling at 1620 RPM. We haven't reached pullout. Data for increased excitation frequencies beyond 6 Hz appears below. In each scenario, given we've adjusted voltage magnitude in the same proportion as frequency, field current remains high, line current remains low, we neither absorb nor supply reactive power, and importantly, we don't reach pullout torque. You get my point. This is the way you operate a doubly fed induction motor. To vary the resultant rotational speed of a doubly fed induction motor, not only must you supply the rotor with variable frequency 3-phase AC, you must also supply it with variable voltage magnitude to account for frequency-dependent inductive impedance. As we wrap this demonstration up, it should be noted that rotor excitation frequency need to be applied in stepped exactly 1 Hz or 2 Hz increments, but changed in a continuously variable analog fashion so the rotor speed meets the exact needs of a specific application. Because that's what this is all about, right? Speed control. Now, some of you might be like, yeah, but why can't you just grab a regular induction motor and an off-the-shelf motor drive and control speed that way? Why'd you drag us through this admittedly cunning application if a motor drive and an induction motor could do the same thing and control speed? True, motor drives do allow speed control, but a doubly fed induction motor presents additional advantages beyond speed control, 3 of which immediately come to mind. Number 1, cost. Note a traditional motor drive must be sized to handle all of primary power, whereas the power electronics devices controlling a doubly fed induction motor only manipulate the smaller portion of rotor power. For this reason, an appropriately sized AC to AC converter on a doubly fed induction motor might be cheaper than a full-size motor drive. 2, it's synchronous. This is an often overlooked fact. Again, hypo and hypersynchronous modes are extensions of synchronous mode, and once rotational speed is established, the 2 electromagnets lock into each other, and as long as load torque remains below pullout, they remain at that specified speed. Induction motors, not so much, because they're known to exhibit variations in speed with changes in load torque. Additionally, while in operation at that desired stable speed, field current can be so managed that the motor neither supplies nor absorbs reactive power. And finally, and most importantly, number 3, it's really cool. Am I right? Check the box with the appropriate response. All right, that is that. In summary, hyposynchronous operation uses fixed frequency 3-phase AC in the stator and variable frequency and voltage 3-phase AC on the rotor traveling in the same direction. As rotor excitation frequency and voltages increase, the rotor slows down. As the name implies, hyposynchronous operation is below regular synchronous speed. Hypersynchronous operation is essentially the same thing, only the rotor rotating magnetic field goes in the opposite direction of the stator. As rotor excitation frequency and voltages increase, the rotor speeds up. As the name implies, hypersynchronous operation is above regular synchronous speed. Before bringing this lecture to a full close, allow me to revisit a point I made earlier in this lecture. I think one of the superpowers of engineers is their ability to call bull when they see it. The superpower, by the way, may be a very poor fit as an officer in the United States Army. The bullshit I'm calling is this. This is not a doubly fed induction motor. This is demonstrably an extension of synchronous mode. So why is it called a doubly fed induction motor? I genuinely don't know. I get the doubly fed part since you're feeding both the stator and rotor. And I obviously get the motor part since it's consuming electrical power and producing rotating mechanical power, my go-to definition of a motor. But induction? This is not induction. This is synchronous mode with all the benefits, i.e. constant speed inside its operational range and control of reactive power, and drawbacks, i.e. more complex starting circuits. So why is it called induction? Again, I don't know. but I can only surmise the clearly incorrect reason it is commonly referred to as such. Let's start with some basic definitions that I hold true so you can see where I'm coming from. What does induction imply? Induction implies that induction is happening. Induction is a changing magnetic field that sweeps through a conductive coil and generates voltage, which generates current, which generates an induced magnetic field, hence the name, which follows the original magnetic field that induced it around and around. Induction motors exhibit changing speed as a function of load torque. Induction only happens in traditional wound rotor induction mode with a cage-like induction rotor. What does synchronous imply? To me, synchronous implies two magnetic fields locked into one another that follow each other around and around. In traditional synchronous, hyposynchronous, and hypersynchronous, there are two magnetic fields locked into one another that follow each other around. Yes, you can vary the speed by adjusting the excitation frequency of the rotor, but once it's set at that speed, the speed should remain constant inside its operational range. So why is this called induction? Only way I can rationalize this clearly wrong title is because you're doubly feeding what wouldn't ordinarily be an induction motor to act synchronously. After all, a doubly fed induction motor acting synchronously is just a repurposed wound rotor induction motor. This would be like buying a Ford Pinto, only to replace the wheels, frame, engine, exhaust system, transmission, cooling, and exterior with entirely modern, high-power efficient components, yet still call it a Pinto because you kept the exploding gas tank. Doesn't mean it's right, but I kind of get where this might originate. All right, before I go off on some other tangent that winds me up, let's call it a day. In conclusion, this lecture examined how a wound rotor induction motor can be repurposed as a doubly fed induction motor. We took a look at synchronous, hyposynchronous, and hypersynchronous operation and explored how varying rotor excitation frequency one could control resultant rotational speed above and below what would ordinarily be considered synchronous speed. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.